Good morning everyone, can you hear me? Good morning, can you hear me? Okay. Okay, so last time I was doing optics with you, but for optics I have recorded the videos and I will post them on YouTube soon. For now I will start with current electricity. Okay. Right, any doubts, anything? I'll start with current electricity today. Good morning. Okay, so I think a little bit of idea you have about current. Yes, you have done this in your lower classes. Current is actually a flow of charge, right? Flow of charges produces current. Flow of charges constitutes current, right? This is what you have learned so far, I think, in your class 10. Okay, so we will develop on this and we will have to learn this a little bit in detail. Okay, so now let's start with that. Charges, a lot of things you have studied about charges in your chapter of electrostatics. You know that there are two types of charges, positive, negative, right? You can have positive charges, you can also have negative charges, right? And a stationary charge produces an electric field, all that. Static, so far we have learned about static charges. Static charges means charges which are at rest. So when we studied about these charges, we studied that they produce electric field, right? So far we have studied about that. Now we will study what happens when these charges are in motion. What happens when these charges are in motion? Okay, so before that I would like to explain what happens inside. Okay, now here in this chapter we will mainly be discussing about conductors, how current flows in conductors. Okay, how current flows in conductors. Okay, when I say conductors, they are mostly metals, right? Conductors are mostly metals. Okay, so how does current flow in metals? What are the charges in metals that allow the current to flow, or because of which the current flows? Okay, so we'll study about that. Right, so let us say this is a conductor. Now if you break this conductor into the smallest pieces, what will you get? You will get an atom. Yes or no? This atom is the smallest unit of matter, right? Atom is the smallest unit of matter. So if you break this conductor into the smallest piece you can possibly get, it will be an atom, right? Even an atom can be broken, but we will not go into that. Atom can be broken, right? So atom, a little bit about atom, you know. Inside the atom there is a nucleus at the center. At the center there is a nucleus, and this nucleus has a positive charge, and surrounding this nucleus will be electrons, right? Electrons will surround this nucleus. Okay, this way. Yes, depending upon the number of the shell, you can also find out how many electrons it can store. For example, a first shell can store only 2 electrons, and so on. It will increase, it will go 2, 8 and so on, right? This, I think, this knowledge you have from chemistry, right? Now if I ask you what is the difference between a conductor and a non-conductor based on this, right? Okay, so first of all I said conductor is what? Conductor are mostly metals. Metals are conductors. and non-conductors will mostly be non-metal. I am not saying all non-metals are insulators or non-conductors, or I am not saying that all metals are conductors, but mostly it will be metals who are conductors and non-metals who are non-conductors, right. Now, what is the difference between the two? On the basis of this diagram, what is the difference between the two? Now, the difference is that, for let me take an example of metal. The best example would be sodium, right. The first example would be sodium. Now, if I draw the structure of sodium, the atomic structure, there is a nucleus at the center again, and surrounding this are electrons in two shells, right, or three in fact. Right, so that way, so we have how many electrons are there in sodium? There are 11 electrons. You should know this. The 11 electrons. So, for the first two electrons will sit in the first shell, then next shell can store 8 electrons. So, right, 8 electrons, and so how many left now? 2 plus 8 is 10. So, 1 left, and that one will sit in the last shell. Okay, but this last shell, this last electron is quite far from the nucleus, and why okay, first of all, why does the electron stay in this shell? Is because the nucleus has a positive charge, electron has a negative charge, so they attract one another, right. And because of this attraction, electrostatic attraction, the electron is forced to stay in this orbit. It cannot go out of the atom if it wants to. But what happens as you go far away from the nucleus, that force decreases, right. And at about this third shell also, the force is quite weak, and this electron that is here alone is free, is not totally free, but it can go out of the atom if it gets a little bit of energy, right. If somebody supplies it a little bit of energy, then it can come out of the atom, right. Such an electron is called a free electron. Okay, free electrons are those who are not bounded to the nucleus, right. They will be there, but if somebody supplies a little bit of energy, then they can come out, right. And in fact, if I keep sodium at room temperature, if I just keep it in my hand also, it will have enough energy. These electrons will have enough energy to come out, because at room temperature it will receive certain thermal energy, right. When I keep it outside at some temperature, let us suppose the temperature of the room is 20 degrees Celsius, then this temperature also, because of this also, this electron will get some energy, and that energy is called your thermal energy. And if it has that much energy also, it can come out, so it will almost become free. So, this electron will become a free electron. So, that is the difference between a metal and a non-metal. What happens in metal? You have lots of free electrons. Metals has many free electrons, okay, many free electrons, but that is not the case with non-metals. Non-metals does not have many free electrons. They are mostly bounded to the atom, right. No free electrons. Okay, so that is the case. Now, what happens, since this electron is free, it can now move around in this conductor. Nobody is going to stop it. The atom cannot pull it, the nucleus cannot pull it. So, these electrons, these free electrons, can move about in this conductor, right. And it is the movement of this electron that produces current, right, Is it clear, the concept so far? Is it clear, or any doubts? So far? Please type in the comment box if you have any doubts. Okay, so that is the brief idea about what happens inside a metal, right. One more thing, I am talking about conductors here. Okay, current can flow not only through metals, it can flow through a lot of different things. It can be metals, it can be liquids. Current can also flow through liquids, current can also flow through gases. Okay, so but what is the difference is that the carrier of current in metals are electrons. Electrons carry current in metals, you can say. In liquids it is the ions, and in gases it is the, again it is the you can say electrons plus ions. Okay, in gases it is both. Okay, now liquids, ions, I think you have studied in chemistry, physical chemistry, you must have studied. When you study about battery, what is there inside a battery? There is a liquid, right? It is sometimes it is copper sulfate, sometimes it is hydrogen chloride, right? And what happens when you discharge or when you ionize this, the copper breaks into 2 plus and 2 minus, and these are the ones who carry the current, right? For liquid, for copper sulfate, it is the copper ions together with sulfate ions that help and carry current. The copper ions will go to the cathode, right, and sulfate ions will go to the anode, and that movement is what produces the current. Is it clear? So that is about liquids. And gases, it will be both combination of electrons as well as ions. Okay, it will be the combination of electrons as well as ions. Now what is an ion? If you don't know what is an ion, see, like I said here, sodium, when I gave example of sodium, right, okay, 2 electrons here, 8 here, and last one here, right? Now like I said, this electron in the last shell is free to come out, so it may come out if it wants to, right? It will come here. So it can come here, right? Okay, now after this electron comes out of the sodium atom, what happens to sodium atom? What does it become, right? So before it was neutral sodium atom, which we write like this, but once the electron, which is carrying negative charge, comes out of the sodium atom, then this sodium atom develops a positive charge. Why does it develop a positive charge? Because the number of protons will be more than the number of electrons when the electron escapes. Okay, so that is why this will become positive, and this is called an ion. Okay, ions are atoms which carry charges, you can say, right, which have excess charges. Sometimes they will have excess electron. In that case, it will be it will show a net negative charge, and sometimes when electrons are less, it will show a net positive charge. Okay, so ions are these. Okay, when the electrons from the metals, when the free electrons from the metal atoms come out from the last shell, then this atom will be deficient in electrons, and as a result of which it will develop a positive charge, and such atoms are called ions. Now they have a charge. Until the electron was here, the charge of the sodium atom was neutral, that means it did not have charge, but when the electron escaped, the charge was developed, and that charge is positive. Is it clear so far? Any doubts? Any doubts so far? Okay, metals, in metals electrons are the carriers, in liquids ions, and in gases both electrons and ions. Yes, any doubts? Any doubts? Okay, so that is the beginning of I mean, that is the brief idea of how current is produced. Right now, how many free electrons, how many free electrons do metals have? Right, how many free electrons do metals have? So to give you a brief idea, metals have. Okay, to give you a brief idea, if you take an area, of 1 cubic centimeter square, if you take an area of 1 cubic centimeter square, right, of a metal, then in this area there will be about 10 to the power 28 free electrons. Okay, free electrons per meter cube, per not meter cube, per centimeter cube. Okay, per centimeter cube of metal there are about 10 to the power 28, sorry, it will be meter. Okay, not 20, just a minute. Yeah, per meter cube there is about 10 to the power 28. So you can see it is a very big number, right? And this is the reason that metals are very good conductors, right? Metals are very good conductors is because of this. Very good conductors, right? Metals are very good conductors is because of the presence of large number of free electrons. Okay, 10 to the power 28, it's a very big number, right? And this is, and these are the electrons which move around in the conductor, and as a result your current flows, right? But one problem is there. See, if you just take a wire, and connect it to a light bulb, you will not get any current, right? If you just take wires and connect it to a light bulb or any appliance, the bulb will not glow or the appliance will not work. Why? Because the current is not flowing there, right? What is the problem inside is that, see, these electrons, like I said, they will be in motion. Okay, let me draw a bigger picture. Right, so these electrons will be in, the electrons inside will be in motion, but the problem is that the motion is random motion. Okay, the electrons are not moving in a fixed direction. Some electrons will go to the left, some will go to the right, some will go to the above, some will go down, some will go northeast, southwest, all that, right? The motion is random. Okay, there is no fixed direction, and what happens as a result, it is as if the motion is zero, or there is no net motion, right? This electron will maybe go here, go up and down, right, like that, understand? But ultimately the displacement will be zero, and because of displacement zero, there is no net movement, right? If you want current to flow, the electron should have some movement, right? But because here the problem is that it is a random motion, there is no net flow. One electron will cancel out the other. If one electron goes to the right, the other electron will go to the left, and they will cancel out each other, right? The effect will be cancelled. So that is the problem with a conductor. The good thing is that it has many free electrons, but the problem is that the motion of these electrons are random motions. Okay, they are random motions, and there is no net movement, right? So that is why if you just take a conductor connected to a source like a bulb or anything, right, you will not get current, right? For that you need an appliance. What is that called? That is called a battery. You need a battery or a cell, right? You can call it a battery or a cell. You need one of these to make current, right, to produce current. Okay, so let me give you an example. What I'm saying is, like, suppose I have a, suppose there are two persons here. Okay, and they are holding a pipe. They're holding a pipe, and inside this pipe there is water, right? Inside this pipe there is water. Okay, there is water. So logically thinking, will the water go anywhere? No, right? Water will stay somewhere in the middle. Neither it will go to the left, neither it will go to the right. So electrons are like that. Without the battery, electrons are also not going anywhere. They are just moving around, but ultimately that movement is random, so you don't get any good result, right? Now what happens if suppose But what happens if I we lower the pipe like that? What happens if we lower the pipe, right? Now in this case what happens? The water will flow, right? It will flow in a fixed direction, it will flow in this direction, right? It will go down, right? So this is the job of a battery. Initially when you have a simple conductor without a battery, this is the situation, right? Without the battery, this is the situation. The electrons are moving around inside, but there is no net effect. But once you connect a battery, you are forcing the electron to move in a fixed direction. You are forcing the electron to move in a fixed direction. Okay, once you connect a battery, you are forcing the electrons to move in a fixed direction. And now once we get a little bit of displacement, once the displacement is not zero anymore, in that case current is produced. Is it clear? Understand? Can you understand from these two examples what I am trying to say, right? So this is the simple example of that. Yes, any doubts? Any doubts, anything? Okay, so that is the job of a battery. The battery does not supply electrons. The electrons are already there inside the conductor. The battery, the use of a battery is just to create a potential difference. The use of a battery is just to create a potential difference, right? So what is potential difference? It's like now see, here water is not flowing because they are at the same potential with respect to gravity, right? With respect to gravity, both the levels of water is at the, I mean they are experiencing the same force of gravity. That is why the water does not flow. But when you tilt the pipe like this, right, the force of gravity, because of the force of gravity, the water is forced to come down, right? So it's like gravity is creating a difference, a potential difference. Okay, so in the same way battery is also used to do that. It's used to create a potential difference so that the electron moves in a fixed direction. Okay, so how does it create? Now see, this longer end of the battery has a positive charge, we represent it with positive, right? That means this is a positive potential, and this smaller line is at a negative potential, right? So what will happen now? Whatever free electrons are there inside this conductor, right, they will be forced by this negative. This negative will force these electron to move around, right? What happens when two negative charges come close to one another? There is repulsion. Yes or no? There is repulsion. When two negative charges come close to one another, there is repulsion. So you can think like that. This negative potential drives the electron. It pushes the electron because of repulsion, and the electrons are now forced to go in this direction, right? And also this positive also attracts the electron, right? Positive attracts electron, so also there it will get help from that, right? So the negative will push the electron, the positive from here will pull the electron. So now you have a direction, you will get a direction in which the electron will move, right? And that is the movement that we want. Once we get such a movement, then we can generate current, right? Our aim is not to make the electron go in a fixed direction. Our aim is just to get a little bit of displacement, right? If the electron, yes, just suppose it starts from here, comes here, right? Still you can see there is a little bit of displacement. It did not go to the original position, right? So even this displacement is enough for us. If the electron just moves like that also, it's enough. We don't want the electron to go in a fixed direction, but even if there is a little bit of displacement, if it does not come to the original place, or it does not cancel out with other electrons, then even in that case current is possible, right? Understand or no? Yes, please type your doubts if you have any. Okay, so I hope that the use of a battery is clear. The battery is not used to give charge, it is used to drive the charge, it is used to create that potential difference, right? since this is at a negative, so this negative will also make this negative and this one positive. So you can imagine as if the tilt is like this. Now the electron is forced to move in this direction. You can imagine like that. Okay. So the job of a battery is to do that, is to create that potential difference. Yes, any doubts? Okay, so that okay. Now direction of current. Direction of current is very important. Direction of current. Now see, initially Benjamin Franklin, okay, Benjamin Franklin, he explained what should be the direction of current or how to take the direction of current. He said that current is in the direction, current is in the direction of flow of positive charges. Okay, current is in the direction of flow of positive charges. So wherever the positive charges are flowing, we will take that as direction of current, and this is called your conventional current. Okay, this definition is called the conventional current, conventional direction of current, or you can say conventional current. Okay, this definition was given by Benjamin Franklin. Okay, current is in the direction of flow of positive charges, but like I said, it is not the positive charges that is responsible, it is the electrons. The electrons are responsible for producing current in a metal. I am talking about metal. In a metal, it is the electrons which are responsible for producing current, and we all know that the charge of an electron is negative, right? The charge of electron is negative. Understand? So what happens here, you may see, it may appear as if these two definitions are contradicting, as if they are opposite, but that is not the case, right? Why? Because see, here inside this conductor, if the electron is going from right to left, the positive charge will go from left to right, right? Because it will be opposite, yes or no? If electron is going to the left, that means there is a positive here and negative here, right? So in the same way, what will happen to positive here? A positive here, that is denoted with P, will be pushed in the opposite direction. Are you understanding this? This is very important. I hope you understand, right? If electron is going in one fixed direction, the positive charge will definitely go in the opposite direction, right? So that's why we still follow this definition. We still follow this definition, and we say that the direction of current is from positive to negative. That means in the direction of flow of positive charges. So in this figure here, I said that the electron is going from left to right, right? So the positive charge will go from, the electron is going from right to left, right? So the positive charges will go from left to right. So the current will also be in that direction. The current is also from left to right. Okay, we are following this definition. Okay, current is in the direction of flow of positive charges. Okay, so remember this, electrons and the direction of current is opposite to one another. The direction of flow of electrons and direction of flow of current is opposite to one another. Okay, is it clear? Even though this current is because of electrons, but the direction is opposite to that of electrons. That part is clear or not? Is that part clear? Okay. Okay, so if you have a circuit like this, if you have a circuit like this with a battery and let us say this is a bulb, right. So with this symbol of a battery, with the longer line represents the positive and the smaller line represents the negative. Okay, so what will happen, the electrons that are inside these wires, inside these red wires that I am drawing here, right, the electrons that are here will be pushed by this negative terminal. Okay, and they will flow in this direction, right, the electrons will flow in this direction. Okay, will flow in this direction, but as per the definition of direction of current, the current direction will be opposite. So the electrons will go in this anti-clockwise direction, right, in this anti-clockwise direction, whereas the current will flow in the clockwise direction. Right, this will be the direction of current. Okay, current, and this is your electron. Okay, so that you have to remember, direction of current is opposite to direction of electron. Okay, is it clear? I hope that is clear. Now one more thing here, even though current has a direction, it is a scalar quantity. Even though current has a direction, it is considered to be a scalar quantity. Why? Because if you want to do mathematics with current, if you want to add current or subtract current, you can easily do it with simple algebra. Okay, you can simply do it with simple algebra. You don't have to use vector algebra. Okay, well, vector algebra we have done in class 11, if you remember, right, a cross b, a dot b, a vector plus b vector, all that. We don't have to use that for current. We can simply add. If there is a current of 2 ampere and 3 ampere that is flowing in the same direction, and if I want to find out the total, I will just add 2 plus 3. That will give me the answer. I don't have to look at the direction in which one current is flowing and the other current is flowing. Is it clear? So even though current has a direction, it is considered to be a scalar quantity, because you can easily add or subtract current with simple algebra. You don't have to use vector algebra. Okay, now what is the direction of current? It is from positive terminal of the battery to negative, right? So from positive to negative. So that's why whenever we draw the circuit, we draw this arrow, right, to show the current. We draw this arrow. This arrow is because we are saying that the current will flow from here, positive, start from positive, and it goes to the negative, right? So that is the direction of current. Okay, so always when we draw a battery and circuit, we always have to show the direction of current, right, and that direction will always be fixed. It will be from positive to negative. We don't have to show the direction of electrons. Okay, electron is just for the explanation, but we mostly don't have to show the direction of electron in a circuit. Okay, but current we have to show. Is it clear? Yes or no? Any doubt so far? Yes, any doubt so far? Okay, so that is the current. Now let us talk about one thing here. Okay, so look at this diagram on the right, let me call this diagram 2. Okay, this diagram shows how an electron moves, inside a conductor when you apply a potential difference. Okay, now one thing I have to explain. Suppose this is a conductor. Okay, conductor can be anything. Okay, conductor can be a wire. A wire is also a conductor. It is made up of metal, right? So suppose this is a conductor connected to a battery. Right, so this conductor is connected to a battery. Now what happens? The electrons that are sitting here inside are subjected to a potential difference, because of these positive and negative terminals, right? So that so this is your positive, this is your negative. So it will appear, this positive will appear here and this negative will appear here, right. So these electrons are subjected to these, okay, these potentials, okay. This negative will push the electron towards the positive, right. So this is the potential difference that is created by a battery, right. And potential difference gives rise to electric field also. You also get an electric field, right. Whenever there is a positive and negative separation, you get an electric field, yes or no. And that electric field starts from the positive terminal towards the negative terminal, right. So you will get an electric field here, which is actually responsible for pushing the electron, okay. Potential difference is just to create that that slope. Remember, for water, when I gave example, potential difference is just to create that, right. But who will do the work? It is the force of gravity, right. It is the force of gravity that will do the work. Here also it is this electric field that will do the work of pushing the electron, okay. Potential difference, when I say create a potential difference, we are just creating a you can say a slope, right. So that the electrons are forced to go there, but ultimately it is the electric field which is responsible for pushing the electron, okay. Electric field, we have discussed about electric field, right. Now one relation I want to give you here. So if the length of this conductor is L, if the length of this conductor is L and the potential difference created by a battery is V, then E is equal to V by L, okay. This relation you have to remember, E is equal to V by L, right. If V is the potential difference. Now whenever you go and buy a battery from a shop, you will see there will be written there 1.5 volt or sometimes 3 volt, right. And if you buy a bigger battery, then this number will go on increasing, right. So 1.5 volt, it is the potential difference that is being created. More potential difference, more current. It's like this, suppose this slope compared to this slope compared to this slope, right. With this slope the electrons will move, but it will be a bit slower, more and even more, right. So it's like that. More potential difference means the slope is more. You can imagine like that, okay. You can imagine like that. If you take a bigger battery, it will have a larger potential, it will create a larger potential difference, okay. And larger potential difference will create a stronger electric field, okay. Is it clear here, yes or no? So in this diagram that I showed you, in this diagram you can see here E, this E here is the electric field, okay, and it is a vector quantity, and you know direction of electric field is from positive to negative. We have discussed in the first chapter, right. Direction of electric field is from positive to negative, okay. Is it clear, yes or no? Potential difference, all that is clear or not? Any doubts, anyone? Now so in this diagram I have shown, so this red line shows the direction in which an ordinary electron will move if you connect this conductor to a battery, right, and because of this electron. Now as I said, even when we apply the electric field, it's not like the electron will go straight in one direction. Why it does not go in one direction? See, I told you there are 10 to the power 28 free electrons in a very small space, right. So if so many electrons are there, what will happen? Collision will happen, right. Collisions will happen, they will collide with one another, right. So this path is because of collision, and it is not only the free electrons, even the ions are there, even the ions are there, right. Even the ions are there. What are the ions? I told you when I gave example for sodium, if I remove the last electron, you get Na plus. So this Na plus is also sitting there inside the metal itself, right. It is not going in anywhere, right. So what happens? Any electron that is moving in this space will either collide with other free electrons, or it will collide with the ions, right. So that is the problem, and that is why electron, this direction of this red color line shows the direction of the electrons. Any doubts? Yes, any doubts? Okay, so now let us find out with what velocity are the electrons moving inside. With what velocity are the electrons moving inside? Okay, we will study about that, and that is, there is a specific name for that. We will study what is the average velocity. Now each electron will move with a different speed, but if you take the average, there is a fixed average, right? So that we will find out now, the average velocity. Okay, now before that, let us imagine we have a conductor again, and we have a conductor where battery is connected, right? In the first one, battery is not connected. In the second one, battery is connected. Okay, so if you look inside this conductor where battery is not connected, you will see the electrons are moving randomly. Okay, they are moving randomly, and their ultimate displacement is 0. Right now, I want to ask you velocity. Velocity formula is what? Displacement divided by time. Yes or no? The definition of velocity is displacement divided by time. So if any object is there that is moving like this, ultimately coming back to its own position, displacement will be 0, right? If there is an object that is ultimately coming back to its own position from the starting point, then displacement will be 0. So in that case, velocity will also be 0. So that is the same thing that happens here. If we take, let us say that there are n electrons, n number of electrons. Okay, let us say that are n number of electrons, right? They have some velocity, they are moving, so definitely they have some velocity. But what happens, since displacement is 0, right? Since displacement is 0, or the net displacement is 0, so the average velocity is 0. Okay, so let us say u1 is the velocity of the first electron, right? u2 is the velocity of the second electron, u3 is the velocity of third, and so on till un is the velocity of the nth electron, right? Okay, so this is the average velocity of the nth electron. Understand? Now, like I said, since these motions do not result in anything, right, they will ultimately cancel one another, right? If one electron is going to the left, other will go to the right, so they will cancel each other. Okay, and ultimately what happens, your average velocity, which is actually your average velocity is written with u vector. Average velocity is u1 plus u2 plus u3 so on till un, divided by the total number n. This will be 0. Okay, why it will be 0 is very important. Like I said, the motion of the electrons are random motion, and the motion of one electron will cancel the motion of the other. If one electron is going to the left, other will go to the right, so they will cancel one another. If one electron is going to the going above, one electron will go down, so they will cancel. So in that way, this average velocity is 0, because there is no net movement, right? There is no net movement. This part is clear or not? This part is clear? Is this part clear, yes or no? Okay, so that is this. Okay, now why I wrote u here, if you remember in class 11 also we did, but before that you did in class 9, the three equations of motion. V is equal to u plus at, s is equal to ut plus half at square, and last one, v square is equal to u square plus 2as. Do you remember this? I hope you remember. These are the equations of motion. Here v represents final velocity, u represents initial velocity, your t represents the time, s represents displacement, and a represents acceleration. Okay, acceleration. Understand? So these are the things we did in class 11 also, right? And even class 9 you must have done this. Okay, so here my reasoning for representing them with u is because I want to say that they are initial velocity, right, before the battery is used. After the battery is used, what happens? Like I said, once you use a battery, electric field is created, like I showed here, right? And whenever an object is inside, whenever a charge is inside electric field, suppose there is an electric field in an area, there is an electric field in an area like this, right, positive to negative, right? If there is an electric field here, and suppose there is a charge somewhere, charge q, then this charge q will experience a force, right? This charge will experience a force, okay, just like if there is gravity anywhere, if there is gravity anywhere, then whatever mass is inside that, whatever mass is inside that area will experience a force, right? Just like we have, if we have earth, if we consider earth, then earth produces a gravitational field, and whatever object is inside this field will experience a force. In the same way, electric field that is produced will exert a force on any charge that is in that area, okay, and that force is given by, you must remember, it's q e, right, and in vector form you write this way. Is this clear, yes or no? This is the charge that is experienced by a charge that is sitting in an electric field E, okay. Is this clear, yes or no? Okay. So now what happens once you connect this battery? Like I said, electric field will be produced, and all the electrons that are there will experience this force. Now, so how do you write Newton's second law? Newton's second law, if you remember, Newton's second law of motion. Newton's second law of motion is what? F is equal to ma, right? This is the equation of motion, or in vector form I can write F is equal to ma vector, right? So we will use this here. Now force is this one, this is the force that it experiences, and a is the acceleration. So acceleration I can write on the left, and this will be equal to F by m. This part is clear so far? So far, any doubts? Any doubts so far? Okay, so that is the acceleration. This will be the acceleration that the electron will be subjected to. This is the acceleration that will be subjected, that the electron will be subjected to. Now let me put the values. So now a will be equal to F, like I said, is QE divided by m, right? This is the acceleration. Now q, what is q? Q is a charge, right? Q is a charge, but in case of electron, what is the charge of an electron? Charge of an electron is written with small e with a negative sign, right? This is the charge of an electron and the value of E is 1.6 into 10 to the power minus 19 coulomb, right? This is the charge of an electron, E with a negative sign, and the value of E is 1.6 into 10 to the power minus 19 coulomb, right? So that is the charge. So let us put that value here. So A will actually be equal to minus E vector divided by m. Any doubt so far? Any doubt so far? Yes, any doubt so far? Why minus E? Like I said, this Q is what? It is a general charge. It is a you can say This is a general expression, right? Q is a charge, general charge, it can be anything, but we are dealing with electron. So that's why instead of Q we are replacing the charge of an electron, and charge of electron is minus E, right? Just like there is pi, you know, the value of pi is 3.14. So E is actually just a just an alphabet that is used to represent this number 1.6 into 10 to the power minus 19, and we know charge of electron is negative, so that is why we write minus E. Clear now or still doubts? Okay, so that is the thing now. Okay, so like okay, now see, once the electron experiences a force, if it experiences a force, it will experience acceleration. And what does acceleration do? Acceleration will increase the velocity, right? When I say an object is accelerating, the meaning is that the object's velocity is increasing. So the initial velocity is u1, this u1 is the initial velocity, right? When there is no battery, then these are the initial velocities, right, without the battery. But once you connect a battery, what happens? Acceleration is produced, and because of acceleration velocity will increase. So how to find that velocity, final velocity? We will use this. Okay, to find that final velocity we will use this. V is equal to u plus at. V is the final velocity, u is the initial velocity, a is the acceleration, and t is the time for which it is moving. Okay, so final velocities, final velocities of n electrons, final velocity of n electrons. Okay, so let us say that the electron, now see what happens, look at this diagram, right? So you see the electron will move and it will collide, something will be there, it will collide, again something will be there, it will collide, right? So between these collisions, let us say the electron moves for tau 1. Okay, tau is a symbol, Greek symbol, right? This is a Greek symbol. So let us say let us pick an electron, let us pick the first electron, and let us say that it moves for a time tau 1 until it collides, and during that time tau 1 acceleration is a. So using that formula you will get final velocity that we will get is u1 plus this part is clear or not, right? We are picking the first electron, and that electron is made to move for a time tau 1, right? It made to move for a time tau 1, during which it is accelerated by acceleration a, and it gets a final velocity v1, and using the first equation we get this equation. Yes or no? Is it clear? Tau 1 is nothing, it's like t1, right? Sometimes we use t1, so here I am using tau 1 because we need it later. Okay, tau, this is this symbol is called tau, right? We have even used this to represent torque, right? If you have read the first chapter, you know torque is written with tau, P cross E. Okay, this is the first chapter, tau. Okay, so in this case tau is being used to represent time. Yes, any doubts? Any doubts, please ask. Yes, any doubts? Okay, so this is the final velocity that the first electron will acquire, right. In the same way we can write for the others also. We can write for V2 the velocity acquired by the second electron will be this, right, and so on. We can write for the nth electron. Okay, is this clear? Is this clear? Is this clear? Okay, so let us find the average of the above velocities, right, and that is given a specific name. It is called drift velocity. Okay, this is called drift velocity. It is written with small v subscript d. Okay, the average of all this, the average of all this, right, is called your drift velocity. Okay, if you take the average of all this, it is called drift velocity, and it is denoted with small v with a d. Okay, so how do we write that? We write v1 vector plus v2 vector plus v3 vector plus vn vector divided by the total n, right. So far it's clear, I hope. Now if we put the value of v1 is u1 plus a tau 1, v2 is u2 plus a tau 2, if v3 is u3 plus a tau 3, and so on, and vn is this is un plus a tau n, right. This part is clear, I hope. Now divided by n. Okay, any doubts? Any doubts so far? Now what I can do here, I can write like this. I can group the u1s together, u1, u2, u3, un, right. I'm just grouping, I'm just making a group, and here the others, what is left now? A tau 1, a tau 2, a tau 3, and so on. So I can take a common from there, and I will get tau 1 plus tau 2 plus tau 3 plus tau n, right, and divided by the whole thing is divided by n. Yes, any doubts? Any doubts? Any doubts? Okay, so now I'll just separate them. I can do this. u1 plus u2 tau vector u3 plus un divided by n. I can do this here, and this group I can make separately. I can do this, yes or no? Any doubts here? I'm just breaking it into two parts, right? Any doubts here? Okay, so now look at this first part. If you look at this first part, right, this part, if you remember, this is 0, right, from above we have shown that this is 0. Yes or no? Somewhere, where is that? Here, right, here we have shown that this is 0. Okay, so this is 0, understand? So we can put 0 here also. So your Vd will be vector, this will be 0 plus a. Now tau 1 plus tau 2 plus tau 3 plus tau n divided by n, this is also a average, this is also an average of what? Average of time, and that is denoted with tau. Okay, any doubts? And this tau is called your relaxation time. This tau is called your relaxation time. Okay, what do you mean by relaxation time? It is the time between two consecutive the average time between two consecutive electrons. Okay, this is the average time between sorry, not electrons, collisions. The average time between two consecutive collisions. Like I said, the electron is not it's not like the electron will move in a straight line, right? So if I consider an electron like this electron will go and hit here, then here, maybe here, like that. Okay, it will hit something here, it will hit something here, right? So what is this tau 1? So in this way we can consider many electrons, right? This electron will go and hit here, it will go there, maybe then hit here, like that. Okay, so what is this tau 1 or tau? It is the average of the relaxation average time between two consecutive collisions, right? See, the electron collides once here, collides here, right? So if I take how much time did the electron move between these two, let us say tau 1, how much time did the electron move between these two collisions, tau 2, and if I consider third electron tau 3, like that, and if I take the average of that, it is called tau, and that is the average time between two consecutive collisions. Okay, how much time passed before between the two collisions occurred, right? Relaxation time is clear to you? Yes or no? Relaxation time is clear? Okay, so that is relaxation time. Now the expression that we get is Vd will be, now if I forget the 0, then this will be a tau, right? Now a also we have derived an expression for a here, right? This is the expression for a, right? This is the expression for a. Now we'll put it, we will put this in the here, we will put it here, and now your Vd will be equal to minus E, capital E vector by m tau. This is the average velocity acquired by the electrons when it is subjected to an electric field. Is it clear? This is called your drift velocity. Drift velocity expression is clear or not? Yes or no? Okay, so that is the thing. Now one thing I want to tell you here is that, see, your electric field look at this diagram. If you look at this diagram, this diagram, right? See, electric field is from right to left, whereas the electron moves from left to right. Okay, remember this direction of electron and electric field is opposite. Okay, if the electron is electric field is acting from right to left, electron will move from left to right. Okay, so that is the thing. Now if you put the values here, if you put the values of the thing that we know, like suppose we put the values, then the average value of Vd is found to be 10 to the power minus 4 meter per second. Okay, this is the average value of your drift velocity. Okay, this is the average velocity of drift velocity. How much? 10 to the power minus 4 second. So whenever you apply electric field, whenever you use a battery for current, the electrons inside are moving with average velocity of about this much, 10 to the power minus 4. Now if you look at this value, it is a very small value. Yes or no? It is a very small value, right? 10 to the power minus 4 means what? It means 0.00041, sorry, 0.001 meter per second, right? This is the meaning of that. Okay, so now if you think that, so if you look at this value, you will assume that the electrons, if the electrons are moving so slow inside a conductor, how come when we whenever we switch on light, right? Suppose you are inside a room and you switch on the light, does it take time for the light to come up? No, right? It happens instantaneously. Yes or no? It happens instantaneously, right? It happens instantaneously. And even though the electrons are moving so slowly, it happens instantaneously. What is the reason? The reason is that it's not like the electrons will start from this end and has to go to the other end, right? Electrons are present everywhere in the wire. Electrons are present everywhere in the wire. So all the electrons will move, right? So when all the electrons are moving, so ultimately the current will be produced faster, right? Because all the electrons are moving. It's not like running a race, right? The electrons are present everywhere inside the track. You can imagine like a running track, and electrons are present everywhere. So once you switch on the battery, all the electrons are moving. So that is the reason that the current flows so fast, right? Is it clear? Yes or no? Is it clear? Right? Even though the drift velocity appears to be very small, we still get current at a very, instantly whenever we switch on, is because of that. Electrons are present everywhere inside the wire, right? Okay, so that is about your drift velocity. Now I forgot a very important thing. Okay, I told you that current is the flow of charges, right? Now there is an expression for current. I forgot. So see, suppose you have a conductor again, and you take an area with you. You take an area with you, and you keep it in this place, right? You are standing here, maybe you're taking this area, right? And you keep it in this place, right? And if I connect this to a battery, if I connect this to a battery, the electrons will flow here, right? The electrons will flow. The electrons will pass through this area, right? So how do you get a magnitude of current? It is the amount of charge that passes through an area or a point held perpendicular to the direction of flow of electron, right. What is current? It is the amount of charge that flows through the area or the point that is held perpendicular to the flow, right. So let us say in time delta t, in a small interval of time delta t, delta q amount of charge passes through this area that you have kept here. You kept an area and you noted the time for delta t. What is delta t? Delta t can be difference between two time, t1, t2 and t1, right. So that is delta t. Now during this time you found out that this many charges were flowing through this area. So in that case the formula for your current will be delta q divided by delta t. This part is clear? Yes or no? Is this part clear? Okay. Delta q is what? Delta q is the amount of charge flowing through the area in time delta t. Okay, that is delta q. Delta q is, yes or no? I is clear. I is equal to delta q by delta t. Is it clear? I hope delta, the symbol delta, you know the meaning of delta by now. It represents change, right. It represents change. Yes or no? Please answer quickly. Okay, so that is the expression for current, right. But see, this value will keep on changing. It's not like 5 electrons were passing once and next time also 5 electrons will pass. It's not like that, right. This value will go on changing. Okay, so that's why it's better to talk about the instantaneous value. That means instead of measuring the current that way, we will measure the current at that time, at instantaneous time. So for that, what do? We decrease this interval. We make this interval very small. And how do we make it small? Using limit, right. You know by the concept of limit by now. Delta t, you make delta t very small. That means you make it almost 0. So if you do that, this expression becomes d dt of q, right, d dt of q. Okay, and this is called your instantaneous current. Okay, is it clear? Yes or no? Okay, so this is instantaneous current. Instead of talking about an interval, we are talking about the instantaneous current by making the interval very small. Okay, so from now onwards, whenever you write an expression for I, it is dq dt, right, rate of flow of charge. So how do you define current? It is the rate of flow of charge through an area or a point, right. It is the rate of flow of charge through an area or a point. Okay, so this is how you'll write the formula for current from now onward, dq dt, right. Understand? And you know how to, this is actually a differentiation, right. Is it clear what is current? What we did today, is it clear, or any doubts? Any doubts, please ask. Yes, any doubts? Okay, so we will stop here today, right? We will leave it with the expression of drift velocity. This is the expression of drift velocity. Tomorrow we will be using this to derive a lot of things. Okay, so I will continue tomorrow. Okay, so that's it for today. I will send you this PDF in a while. You can download them. Okay, notes, I would suggest please make your own notes. If I make the notes now, I'll not get time. Okay, so that's why maybe later I will give it to you, but for now I think all of you have books, so please follow from that book. And if you have any doubts in the book also, you can send me a screenshot of the points or the pages you have doubts. I can explain that. Okay, I'm not giving any notes for now. And also I hope you know your exams, your final exams will be held in March and April, so better start studying. Okay. Okay, so that's it.